Hello, this is Mr. Sorrentino again, and this video I'm going over section 3.2 of the Math 31 textbook, which deals with solving quadratic equations and also deals with quadratic functions, zeros, and models, because all these things are closely related to each other. Because ultimately, I want to be able to solve any quadratic equation that's given to me, and as we're going to see as we go through this, in many instances we're going to be treating it as finding the zero of a quadratic function. Solving quadratic equations and or finding zeros of quadratic functions are in essence the same thing or the same procedure. Just requires maybe a little bit of setup to go from one to the other. So let's look at example 1 first before we get to this idea of equation solving principles for quadratics. Because it kind of brings up the first instance that we kind of did talk about. If I'm asked to solve a very basic quadratic equation, like this here is a very basic quadratic equation, and I'm going to explain what the difference between a basic quadratic equation is and one that isn't so basic. Just like we did for other equations, my goal is to get x alone, and to get x alone on one side of the equation, I essentially follow my order of operations in reverse. Now the only thing that's going to be different is that we now have to handle an exponent as well. But so if I'm reversing or undoing my order of operations, the first thing I want to do if I had x squared minus 8 equaling to 1 is that I would want to get rid of any additions or subtractions first. So I would add 8 to both sides. And so as a result, I'm going to have x squared. These would cancel, leaving me with 9. X is still not alone on the left-hand side because that square is attached to it. So I had to think, well, what do I need to do to get rid of a square? Well, the opposite of squaring is square rooting. When I start dealing with numbers, though, I have to be aware of the principle of square roots. If x squared equals k, then x equals the square root of k, or the opposite of the square root of k. Because remember, a square root symbol only produces positive results. But if I think about it, there are two different numbers that I can multiply together and get 9. 3 is one of those numbers, but so is negative 3. So those are the two answers I would expect to get for this, plus or minus 3, which of course I could write as x equaling 3 or x equaling negative 3. Because again, if I take 3 and square it, I would get 9 because 3 times 3 is 9. If I took negative 3 and square it, which is how you would write it on a calculator too, it has to be in parentheses, that would also equal a positive 9. Please do not write this on your calculator, and I'll show it on the calculator. And then we show the attached LCD screen. A lot of students confuse writing negative 3 squared. That's how you write it, and it's a positive 9. Some students will write it as negative 3 squared. That's what they think it is, and they end up with negative 9, and they don't realize they're making that mistake, or they are doing this as part of a calculation and don't notice that the mistake was been made. The reason for that is this top one here is negative 3 squared. This bottom one is the opposite of 3 squared. And that's one of the reasons why you see the negative symbol down here has the parentheses around it, kind of reminding you that if you're planning on squaring anything or raising anything to a power that's negative or doing anything with a negative, you might want to have that in parentheses to handle it correctly. Because the reason is, this second one, if I wrote it as that, this is interpreted as negative 1 times 3 squared. And according to the order of operations, squaring gets done before multiplying. So the calculator does that. The calculator always obeys the order of operations. So if you're entering it in this way, that's the answer you're going to get. This is not negative 3 squared. This, however, is. So the moral of that story is to be careful how you put things in your calculator, especially when we get into some techniques we're about to use here. But with that principle of square roots, I could just basically solve really basic quadratic equations using the same procedures we used before. However, most of the time we don't have a situation like that. If I just scroll down a little bit here, what if I have an equation that looks like this? Notice this one has an x squared term and an x term. Those terms cannot be combined in any way. So I basically have two different terms I have to consider here, and there's no way to combine them. And therefore, following basic techniques of undoing the order of operations becomes impossible to do for these. And that's where a lot of students will also start making mistakes. They'll try to do basic techniques on a non-basic situation. So I had to start using other techniques for this. And we're going to talk about 3 different techniques we can use for quadratic equations. 2 of them are centered around the other principle up here, and I want to talk about that as we get in, before we get into those methods. It's the principle of zero products. Sometimes it's known as the zero product property. And the zero product property simply says if two things, two quantities, they're showing it as, basically constants here, but any two quantities when multiplied together and I get 0, one of those has to equal 0, or both. And vice versa. So that's the only number for which that works. If I have two things multiplied together and I get 2, one of them doesn't have to be 2. I could have like 4 times a half and get 2. I could have a whole bunch of different combinations to multiply together and give me 2. 0, on the other hand, if I end up with the product being 0, one of the numbers or one of the quantities has to be 0. That's the only way to get it. So with that principle in mind, we could start using some techniques that kind of center around that. And so let's have a look at the techniques that we can use to solve quadratic equations. So if I have an equation that looks like this, and basically, a lot of times we're talking about quadratic equations set equal to 0, which doesn't take much to take an equation like this and set it equal to 0. Or I can think of them as quadratic functions, and I'm looking for their zeros. If I'm trying to deal with situations like that, there are 3 ways of handling of them. I can use a process known as factoring. The issue with the way of using factoring, which I'm going to demonstrate, but the issue with this one is it only works when there are rational solutions to the equation. Factoring becomes a way that we kind of shy away from a little bit. Most people do, because of the fact that, well, until I solve the equation, I don't know if it's going to have rational solutions. And if this is a method of solving the equation, that means that, if it doesn't have a rational solution, factoring is not going to work. It doesn't mean there's not going to be a solution, it just means that the solution is not going to be rational. And therefore, I would try to do this method and find out only that the method doesn't work. If the method doesn't work, I cannot conclude that there's no real solution or is going to have complex solutions. And even if I come to that conclusion, I still want to figure out what those solutions are. So factoring becomes a situation that, if you're able to figure out quite easily what the factors would be, or if there are no factors, not even bother trying it, then it's really, not worth your time to go into it too much. We're still going to show what it does and how to go about doing it, because some of the factoring techniques we'll talk about are useful when we get into dealing with solving polynomial equations. But factoring as a methodology, is impractical. And just because it doesn't work doesn't mean I'm not going to have any solutions. Completing the square, it's good because it always finds a solution, real or non-real, or rational or irrational. However, this one here is, most people find it complicated. And it's complicated because there's a lot of rules that have to be used for it. Again, I'm going to go through it. There's a lot of concepts behind it. It does work nicely and actually takes an equation that looks like this and rewrites it as an equation that you could use basic techniques on, which makes that nice. But there's a lot of things you have to do to make that happen, and again, sign issues and other such things become problems with it. The most preferred method is the quadratic formula, because the quadratic formula basically becomes a plug and chug method. It's a formula where if you plug the right numbers in the right places and you do your computations correctly, you're going to come up with the correct solutions. And, so that's the preferred method for that reason. But there are issues with it, Again, some issues that come up with that is substitution errors. And most of those have to deal with, plus or minus. So that's one of the first things that issues. Sometimes students will put in a number that's positive, it should be negative, or vice versa. And the other ones, of course, is computation errors. Not following the order of operation, not typing it into a calculator correctly, things of that nature also come up with this. So I'm going to go through these three methods. You're expected to know how to do all three methods. However, if you're not told to use one method over another in a problem, you can use any method you want. If you're told to use a specific method, then you have to use that method. Okay, so let's go through the three methods by doing some examples. The first method is to use factoring. And if you've gone through an Algebra 1 course in more recent years, because this used to be something that was reserved for Algebra 2, now it's subject matter that's focused more on Algebra 1 curriculum. It certainly is something that if you've gone into Algebra 2 at the high school level, you certainly have seen many times by that point and practiced it quite a bit, is to use the factoring method. The factoring method, I have to have a situation where the format of the problem is written in ax squared plus bx plus c equaling 0. It has to be set equal to 0 because the factoring method does use the zero product property. My goal is to transform this into two binomial quantities. So I want to factor it into two quantities, like, some number times x plus some other number, and some other number times x plus some other number equaling 0. And then I could say simply, well, this has to equal 0, and I get one answer, and this equals 0, and that's another answer, and that's it. So that's the premise behind it, because again, if the product between those two quantities equals 0, one of them has to equal 0, and then I just test out what makes each one of them equal to 0. That's it. So as a case in point, I want to factor the first one. Now before I start using factoring as a method, I have to have it set equal to 0. One of the big first issues that students have with this is that they don't set it equal to 0 first, and that causes problems. So I'm going to set this equal to 0 by subtracting 1 from both sides. So I'm going to have 2x squared minus 11x plus 12 equaling 0. The method I use, there's different methods that are taught in various textbooks, and a lot of high school textbooks, and even this one to a certain extent, they show methods that are kind of more trial and error. I prefer using something known as the AC method. And I'm going to show what that is as I do these two of them. The AC method's a little bit more direct because it lets you try to list the correct factors in a way that you can start saying, okay, well, what's going to give me ultimately the middle term? The AC method comes from these letter designations, A being the number attached to the x squared, B being the number attached to the x, and C being the constant term when it's set equal to 0. And so what I'm going to do with this is I'm going to calculate what AC is, which means A times C. In this case, it's 2 times a positive 12, which is 24. So I want to list the numbers that when multiplied together would give me 24. And I mean, and the bigger this number is, obviously, the more combinations you have. So I'm going to write out the entire list. However, if you recognize the combination that you're going to need, great. You don't have to write out the entire list. It makes this a little less work. But I'm going to write all the numbers that would give me multiplied together to give me 24. And so that's my list of numbers. Technically, I should probably have more parentheses around these. But there's my list of 8 combinations. And the factoring method, we're only assuming usually integers as we do these. There's 8 combinations that multiply together to give me a positive 24. Notice that 4 of them contain both being positive, and 4 of them contain both terms being negative. I want the one that gives me the b term. Which one, when I add those two terms together, gives me a negative 11? Well, that would be the minus 3 and minus 8. A negative 3 plus a negative 8 would give me that negative 11, or at minus 11 as the middle term. And so what that allows me to do, give myself some more room here, is that allows me to now split the middle term into, a minus 3x and a minus 8x. So I could rewrite this up here as 2x squared minus 3x minus 8x plus 12 equaling 0. Because the AC method transforms this into a situation where I could use another method known as a group and factor. Now, it seems like I'm taking a extra long time for this, and that's just because I'm explaining as it goes along. But if you were sitting here doing trial and error methods, especially if the numbers get any bigger, especially like, 24 there, if I start getting more numbers that are even bigger than that, then I'm going to have even, more to try out. I mean, and do trial and error. Whereas this, lets me consider them in a much more direct way, and I can come up with the right combination a little faster. Group and factor means I'm going to take this and I'm going to split this into 2 groups of 2 on the left-hand side. And what I want to do now, factoring these 2 smaller quantities is much easier than factoring a 3-term quantity. In the first group, I had to think, well, what will factor out of both 2x squared and a minus 3x? Well, I can factor out an x from that. So I can factor out an x, leaving me with 2x minus 3 in the parentheses. For the next quantity, I want to do the same thing, but I also want to keep in mind that when I factor whatever I factor out of the second quantity, I would like this quantity to repeat again. And if I factor out a minus 4 or a negative 4, negative 8x divided by negative 4 is a positive 2x. Positive 12 divided by negative 4 is a minus 3. Now this looks more like something I would get when I'm doing some distributive property, because now I have 2 groupings that both have a multiplication of 2x minus 3. I can then factor that out of both of these groups. And what I'm left with is, of course, once I factor this out, I'm left with the x, I'm left with the minus 4, and now it's factored. So that's the factoring process. The left-hand side is now factored. So I've now been able to rewrite 2x squared minus 11x plus 12 as the multiplication of 2 binomial quantities. Well, the product of those 2 binomial quantities equals 0. So for that to happen, by the zero product property again, 2x minus 3 has to equal 0, or x minus 4 has to equal 0. So now I have really simplistic linear equations to solve. I would add 3 to both sides of the first one, and then divide by 2. So x equals 3 halves, or I could just say 1.5. That's one answer. Or adding 4 to both sides, x would equal 4. So my two solutions, and since it's a second degree equation, I do expect it to have two solutions. My two solutions are 1.5 or 4. And that's how you would use factoring. Now, I want you to try B on your own before I go over how to do it, and I want you to see if you can come up with the two answers for B. Well, for B again, I could try to factor the left-hand side, but once I factor it in any way, I'm going to try to use the zero product property. If I don't have it set equal to 0, I don't have it set up to do that. So again, I'm going to start off this problem by subtracting 36 from both sides to get this set equal to 0. Now I'm going to use, again, this being A, this being B, this being C, I want to do the AC method, so I'm going to figure out what AC is. And whoa, my AC disappeared. I'm going to do AC, which is 6 times a negative 36, which gives me a negative 216. So I want to come up with all the possible factors that would list out to be negative 216. So I'm going to list them down here. Again, if you know any shortcuts or you happen to kind of already know what's going to be needed, then you can shorten this, but I'm going to list all the factors for our sake here. It can take a while to do, but I came up with the entire list of all integer factors of negative 216. And so as you can see there's 16 different combinations here. I want the one combination that's going to give me a negative 19. And so when I take the two terms that I have in these lists and I add them together, I want to get negative 19. And that'll happen when I have 8 and negative 27. 8 plus a negative 27 is in fact negative 19. So that's a combination that I want, and that's the combination that I want to split that minus 19x into. So when I go to solve the problem further and I rewrite the equation, I'm going to have 6x squared plus 8x minus 27x minus 36 is equal to 0. And now I'm ready to do that group and factor. So I'm going to group the first two together, I'm going to group the second two together, and I'm just going to try to figure out, well, what'll factor out of the first group. Both of them will factor out an x, but I can also factor out a 2. So I'm going to factor out a 2x, leaving me with 3x plus 4 inside the parentheses. I want to factor something out of the second group, and I'm looking for this 3x plus 4 again, and so that kind of helps direct me a little bit. Well, if I factor out a minus 9, or a negative 9 from that second group, I'm going to get 3x plus 4 in here. And again, this is all set equal to 0. And since I now have these two groups, both of which have a multiplication of 3x plus 4 in there, I can factor out that 3x plus 4, which would essentially cancel these guys out, and it leaves me with 2x minus 9. Recognize that there's still multiplication going on here. So now the equation I have, which was 6x squared minus 19x minus 36 is equal to 0, can now be written as 3x plus 4 times 2x minus 9 equal to 0. So I've now been able to rewrite that as a product. And being written as a product now, I can now go back and use the zero product property since it's set equal to 0. And based off of that, I can say, well, 3x plus 4 would have to equal 0, or 2x minus 9 would have to equal 0. And so if I go through and solve both of these, subtracting 4 from both sides of the first equation, dividing both sides by 3, I can write that as negative 4/3, which is the same thing as negative 1.3 repeating. Or I could have had the 9 added to both sides of the second equation, and then divided both sides by 2, which gives me 9/2, which is 4.5. And those would be the two solutions for this equation. Both of these are rational solutions. They can be written as fractions, which I clearly do show you, or if they're decimals, I either get a repeating pattern of some sort or a terminating decimal. And I'm not going to get into the calculator stuff because the methodologies are the same as ones I showed in previous videos, except now I have a quadratic involved. But I do show some pictures of how you could use either the intersect function, or you can use the 0 function on your calculator menus to take the graph of this, which we're going to talk about more later, and you can find out where through the right intersections what the solution should be. So that's how you would use the factoring method. Again, kind of complicated because one of the issues is you have to make sure that you're considering all factors. Sometimes students don't, they don't look at numbers like 8 times negative 27. They just go with some basic numbers, and they may skip some possible combinations that may give you that negative 19, and therefore they do a lot of looking and don't really get further into the problem. Or it could just be that the fact that there isn't a combination that's going to do that, and the solution might be irrational, which means that simply that this method doesn't work, and that's all. That doesn't mean there's no solution. It means that the method doesn't work. So now let's get into the two methods that do work. The first of which is completing the square. So let's talk about that next. So in your textbook and in your notes here, you have this little box here that kind of describes the procedure for completing the square. But here's why it works. I'm going to get into that a little bit before we start getting into the procedure. The premise behind this procedure you have in there is basically the whole idea behind a perfect square binomial. And let's show what that is. A perfect square binomial is one that's usually written in this format: x minus a quantity squared. Well, if I write this out by foiling it, I would get x squared minus ax minus ax plus a squared, which is x squared minus 2ax plus a squared. It has a very specific format, and that format is that, and maybe I should use a different letter. I'll use D's instead. Let's make all these D's because I want to still use A, B, and C as the values. When I look at the numbers that represent the standard format, I have a 1 here, which is what my A value is. My B value, as compared to what my C value is, I can see that the B value, or the C value, is basically 1/2 the B value squared. And when I go through this procedure, what I'm looking to do is basically show that I want to get into a format that, if I have it so that this is true, then I should be able to rewrite it as a perfect square binomial. So essentially, if I have a trinomial with this kind of format where this leading term is a 1, I have some number in front of the x, and the third term is simply the middle term divided by 2 and then squared, I can rewrite this as x minus b over 2 squared. So when I go through and do this procedure, first I have to make sure that I have a leading term of 1 because it won't work unless I have that. Secondly, what I have to do is I have to create a situation where I have a trinomial that has a term on my x such that when I look at the third term, the constant term, it's going to be half that middle term squared. And if I can do that, I can rewrite it as something that looks like this. And then I can use basic equation solving strategies to solve it. So let's have a look and see what that means when I go through and do this down here. So x squared plus 6x plus 10 equals 6. One of the nice things about the completing the square method is that I don't have to get it set equal to 0. As a matter of fact, I want it set equal to some sort of number. Now, when I look at this here, I do have the leading term as 1. So a equals 1, great. B equals 6. I want c to equal 1/2 of 6 squared. So 3 squared or 9. Notice I don't have that here. I have a 10. So I either have to adjust for this, or I could just usually start off by subtracting, the c term from both sides and then putting in a new c term. Or I could just say, okay, well, to go from having this being a 10 to being a 9, all I really need to do is subtract 1 from both sides. So what I can do at this point now is rewrite this and say, okay, well, I'm going to have x squared plus 6x plus 9 equaling 5. What's on the left-hand side now is a perfect square trinomial, which is the result of a perfect square binomial. And so when I look at this, realizing that, well, b over 2 would equal 3. That's the number that should be next to my value whenever when I get this rewritten as a perfect square. So basically, this can be rewritten now as x plus 3 squared, and that equals 5. Notice I'm going from having an x squared term and an x term to just having an x term. And if that's the case, I can use basic equation solving techniques at this point. Now that x is inside of a parenthesis and being added by 3. So for me to be able to start moving that plus 3 away from the x, I got to get rid of the parenthesis. Well, the whole parenthesis is being squared, so to get rid of the parentheses, I have to be able to get rid of the square. So the first thing I'm going to do to this is I'm going to square root both sides. Remembering that if I'm doing this and I don't previously have a square root in there, I got to put that plus or minus symbol in. So this ends up being that x plus 3 equals plus or minus the square root of 5. Although I can plug the square root of 5 in my calculator and get some decimal answer, the square root of 5 is irrational. If I'm writing it in some sort of decimal format, I'm rounding it off so it's an approximate value at that point. Most of the time you're going to be asked to provide exact solutions, which basically means in our purposes, leave the square root of 5 as is. X is not alone, though, so I had to go back and say, okay, well, what do I need to do now? Well, I need to subtract 3 from both sides. Since I really didn't do anything with that square root of 5, it really prevents me from combining anything because this is a radical term, this is a non-radical term. So my solution is negative 3 plus or minus the square root of 5, which I could state separately as x equals 3 plus the square root of 5, or x equals 3 minus the square root of 5. And as I said, in most circumstances, I do expect to get two solutions from the quadratic equation. We'll get into knowing whether or not we're going to have one or more and what kind they're going to be in a moment. But those are the two solutions to this. So, and again, I do show some graphics in your notes about how to handle using the calculator to find out and check your work. One way, of course, to take these two solutions, plug them in for x, and then see if you get the left-hand side of the original equation to equal 6. And if that's the case, well, then you're good. But anyway, so right now, that's how we do this first one. Let's try to do one that's a little bit more complicated. Let's look at B. B starts off a little bit more problematic because the whole premise behind this perfect square binomial and perfect square trinomials is I need to have a leading term of 1. Currently, I do not have that. I have a leading term of 4. So the first thing I'm going to have to do is I'm going to have to divide everything by 4. So both sides. So I'm going to have x squared minus 4x. 50 divided by 4 is 12.5. And 6 divided by 4 is going to be 1.5. When you start having decimals or possible fractions in here, that's another thing that causes some confusion and calculation errors. Also, along with that, you also have to be aware of the fact that, when you deal with this term with the x, you might end up with fractions when you're looking to see, okay, what's 1/2 of b, or whatever the case might be. So there's a lot of fractions and decimals that appear with this, which makes it even more complicated for some students. So the other way of doing completing the square method, before I would say, okay, I took half of the b term, squared it, and saw what that was and what I had on this side. The other way of handling it is say, okay, well, for the time being, I'm just going to get rid of the constant term on the left-hand side. I'm going to subtract 12.5 from both sides. That's going to give me a negative 11 over here. So in some cases, when you start off, some fractions might disappear, and sometimes you might end up getting more of them. Remember, we want this term over here to be 1/2 of this term squared. So if I take half of this term, I get negative 2, and I square it, I'm going to add 4 to this side to make that a perfect square trinomial, which means I also had to add 4 to this side to keep the equation balanced. And so, this is my b over 2 value right here. So with that being said, having the x squared minus 4x plus 4 on this side is the same thing as me having x minus 2 squared. And that equals a negative 11 plus 4 is a negative 7. Again, the whole premise behind doing this is it turns a situation where I have an x squared term and an x term, which is a non-basic quadratic equation, into a basic quadratic equation where I could just use basic solution techniques to solve it, basically undoing your order of operations. So here, I have a minus 2 attached to the x, but that's all inside the parentheses, and anything inside the parentheses can't move until the parentheses go away. Since the parentheses are what's being squared, they can't go away until the square goes away. So I'm going to square root both sides. Remembering I have to square root the right-hand side and put that plus or minus symbol in there. So what I have is x minus 2 equaling plus or minus the square root of negative 7. And recognizing that the square root of negative 7 is going to be a non-real number, that's the same thing as having plus or minus I times the square root of 7. So notice I'm getting a complex number here as a solution, because the last thing I'm going to do here is add 2 to both sides. And I'm going to end up with x alone on the left. 2 is a real number. Square root 7 times I is a non-real number. I can't combine them. So I'm going to have 2 plus or minus I times the square root of 7, which of course is the same way of saying either x equals 2 plus I square root 7 or x equals 2 minus I square root 7 as my two solutions. Again, we leave radicals alone to make sure that any irrational solution is written exactly. Since we do have a radical involved, we tend to put the i's in front to indicate that the I is not being square rooted as well, because that's going to be that'd be a different circumstance. And there's my solutions. Both of these, if I had tried to do factoring as the methodology of solving it, I would have tried and tried and tried and nothing would have worked. Again, that doesn't mean there wasn't a solution. I found solutions, and I had irrational solutions. Over here, I have complex solutions. So neither one of them are necessarily rational numbers. So I'm not going to be able to use factoring as a method to solve those. So this technique works in finding any of these answers. It would also work as well if I was trying to find things that would work with factoring. So keep in mind that completing the square could also produce two real numbers as well, or two rational numbers, integers, fractions, whatever the case might be as well. But it's a methodology that works no matter what kind of answers you expect, whereas factoring only works if you expect rational solutions. The last one is the most preferred method, and that's using the quadratic formula. So let's have a look at that one. The quadratic formula is another instance where I have to have an equation set equal to 0. I mean, a lot of people get themselves to memorize this formula: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you've been through any kind of high school level algebra course or algebra 2 course, you probably even have this already burned into your memory. The biggest issues with that is a lot of students forget the first part, is that for this to be true, for x to equal this, you have to have a quadratic equation set equal to 0. And if you don't have it set equal to 0, you have to do that first. The other issue, again, is making sure that you're doing your computations and substitutions correctly. So, and a lot of times the students who try to put too much in their calculator at once are the ones that make the biggest mistakes with this. They think, well, if I got my calculator to do most of the work, I'm going to come up with the right answer. But if you don't put it in right, you don't put parentheses where you might need to have them, it's going to cause issues. So, I would say make sure you're showing enough work and doing enough of the computations, separately from each other, so that you can discover any possible issues when you go along the way. Because a lot of times when you're asked to solve equations using this, you're going to come up with real solutions. If every single time you're coming up with a non-real solution, I'm going to probably say you're probably doing it incorrectly. You might expect one here and there, but under most circumstances, you should expect to get real solutions, especially if you're dealing with a situation where you're using real measurements and things like that along the way. So let's see how we use the quadratic formula here. Again, it's a little bit more straightforward. It's a little bit more it's a little bit less time intensive. It's a really nice thing to use. So when I look at part A, let's focus a little bit more on part A here. keep the formula hopefully appearing it. I don't have an equation set equal to 0. So the very first thing I have to do is set the equation equal to 0. So I'm going to subtract 3 from both sides. And now I'm able to use the quadratic formula because I now have a proper A, B. Notice that B is a negative 16 and C is a negative 3. Those signs are important because now when I go to use the quadratic formula, X is going to equal, the negative is part of the formula, B is negative 16. So notice that just because B already had a negative there doesn't mean, well, that I'm just going to use that negative for the negative I have in the formula. No, 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 nay, nay. That negative here is part of the structure of the formula. This negative is part of the number. I have to include both. Students forget that and end up having a wrong sign there. Plus or minus negative 16 squared. Now, sometimes students don't recognize this. They put in their calculator wrong and get a negative value for that negative 16 squared. You square a number, and it's a real number, and you're not going to deal with any situations where you have a quadratic equation without having all real numbers in this. You're going to get a positive number there. And if you're doing a bunch of calculations all at once, you may not notice that it was negative, and then when you subtract the 4AC, you end up with, something that, ends up being negative or being the wrong number, and that's where your error lies. Minus 4 times A was 16, times C, which is a negative 3. Again, sign errors are a big thing that students often make mistakes with on this, over 2 times 16. So I would definitely say show your substitution so that you make sure you have this right. That's going to be 16 plus or minus the square root of negative 16 squared is 256. And 256 minus 4 times 16 times negative 3 is 448. 2 times 16 is 32. Now, you should definitely explore and see whether or not 448 is a perfect square. You quickly find out it isn't. And here's where we go into some of the rules we had used before. We didn't focus any major attention on them, but I want to be able to simplify this. The 16 and 32, I could do some cancellation with that as long as, with several numbers, as long as I have the same factor for the square root of 448. 448, I could rewrite it as the product of two different square roots. The biggest perfect square that comes out of 448 is 64. Now, you may have to do this in stages, but 448 is 64 times 7. 64 is a perfect square. 7 isn't. So, let me scooch this down a little bit. So I can rewrite this now as x equals 16 plus or minus square root of 64 is 8 times the square root of 7 all over 32. 16, this 8 in front of the square root of 7, and 32 are all divisible by 8. And if I divide each one of those by 8, I'm carrying through the distributed properly correctly, and or I could just think of it as saying, do an extra step and say I'm going to have 16 over 32 plus or minus 8 square root of 7 over 32. which is going to give me a 1/2 plus the square root of 7 over 4. Sometimes it might even be written if you didn't split them up, you could say, okay, well, I could divide out the 8, so that's 1, that's going to be a 2, that's going to be 4, and I could have said I'm going to have 2 plus or minus the square root of 7 all over 4 as well. They're both the same thing. These are both acceptable answers with the minus sign there. So long as you would be able to evaluate both of them. And those are exact answers. So that is the solution to the first equation. It's an irrational solution. That square root of 7, for me to make it more numeric and get rid of the radical, I'd have to put it in my calculator and round it off because it's irrational. So, again, you're often going to be asked to provide exact solutions, so I'm going to leave that radical alone. Let's look at B now. Scooch over a little bit this way. It is set equal to 0 already. That's good. So I don't have to do that first step. So now, this is A, this is B, this is C. So based off of the quadratic formula, X is going to be, again, that negative is part of the structure of the formula. B is -4. Plus or minus the square root of -4 squared minus 4 times 5 times 1 all over 2 times 5. -4 is a +4. -4 squared is 16. 4 times 5 times 1 is 20. 16 minus 20 is a -4 all over 10. So I have 4 plus or minus I square root 4 over 10, which is the same thing as 4 plus or minus 2I over 10. I could either write this as 2 plus or minus I over 5, everything divided by 2. Or I could say this equals 2/5 plus or minus 1/5 I. And then I can separate them into two separate answers if I want to, but generally this would be the solution to that equation. So a non-real result. Again, you could get real number solutions when you use the quadratic formula. These are I'm just showing instances that if you try to use factoring on any of the things from examples 3 and 4, it wouldn't have worked. Now, the textbook, and I have the notes here for it, they go into the discriminant and things like that, and I show some calculator stuff you could do the discriminant with. Let me just show it a little bit. The discriminant, though, is that b squared minus 4ac that you see underneath of the quadratic formula. I don't find any, and I'm not going to have you do anything where that alone would be, that you just have to do that. I mean, I can still ask the same questions, because if I say, okay, well, what kind of solutions would you expect from this? Well, if you start the solution process, you can figure out what kind of answers you're going to get. It just kind of lets you know, though, like, okay, well, obviously when I got to this point here, in example A, I got to this part right here, it having a positive number there that wasn't 0, I mean a non-zero number, that just basically told me I'm going to expect to have 2 real solutions. Doesn't let me know if they're going to be rational or not. Matter of fact, since 4/8 is not a perfect square, I'm going to know they're going to be irrational. I'm going to have 2 real solutions. It stands to reason if I ended up with some number like 16 plus or minus the square root of 0, which your discriminant 0 over 32 in this case. Well, if I square root 0, I get 0. Adding or subtracting 0 doesn't do anything. That means I would have one solution to this quadratic equation, which can happen. Most of the time you're going to have 2. But if you end up with a discriminant equaling 0, that's going to give you one solution. And we usually would consider that to be a double zero, or a double root, and sometimes called. Of course, if you end up with a negative as your discriminant, you're going to have two non-real solutions. And that's what that box is showing you. You don't have to do it as a separate entity. You may not want to do the entire calculation if that's all you're being asked, but it's something to consider when you're solving equations. I usually don't ask a whole lot of questions on quizzes and tests of, well, not quizzes and tests are just, okay, how many solutions you're going to get here. I'm just going to usually say solve this, and then you should kind of know what kind of answers you're going to get based off of what that discriminant is, and that's kind of what the calculator stuff and everything goes into in your notes as well. So I'm not going to say like spend a whole lot of time on the discriminant stuff. Be aware it is part of the quadratic formula, and you could go through and do things to figure out what the discriminant is. I kind of show some things here, but that's not as important. Let's look at some instances here where I can apply the use of solving some quadratic equations. So for example 5, the width of a rectangular room is 23 feet less than its length. The area of the room is 990 square feet. What are the dimensions of the room? Now we had done a problem like this beforehand that dealt with perimeter. Perimeter deals with standard units, whereas area deals with square units. And if I remember that, you can see here the square footage. It's square footage here. That means that chances are when I deal with formulas dealing with area, since we're talking about area, it's going to be probably quadratic in nature. It's going to be degree 2. It's going to have squaring involved. So, and we had done a problem like this before. It's a very similar setup. I have a length and I have a width, which is just 23 feet less than the length. I like to have everything in terms of one variable because I can solve those equations easily. When I get multiple variables, that's where things go awry, and I need other techniques to solve them. The area of any rectangle is length times width. They expect you to remember that from your grade school days because it's something you do talk about in several courses of math in elementary school, and if you had any high school geometry, you've certainly seen it again. But in this case, my length is L, my width is L minus 23. So that's my formula for this. So if I use the values that I have in here, I know the area is 990. L times L minus 23 is L squared minus 23L. This is a quadratic equation, which I expected. It's also one that has both an L squared term and an L term, which means I cannot use basic techniques to solve this. I have to use one of the three we talked about. Now, doesn't matter which one that you choose to use, okay? Just making sure that whichever one you choose to use, you use it correctly. So for instance here, I'm going to use the quadratic formula on this. I'm going to make that decision. So I know I got to get this set equal to 0. So an equation for this would be L squared minus 23L minus 990 equal to 0. If I also chose to use factoring, and I would expect to get some sort of rational solution from this under most circumstances, so I could even try factoring if I want to, but 990 has a lot of different factors. And it would take me maybe a little while to figure out which combination would give me a negative 23. So I may not want to necessarily go that route. But along with that, I want to be able to say, okay, well, I'm going to use a quadratic formula, recognizing that, I have a 1 here, this is B, and this is C. Again, a lot of people tend to shy away from completing the square, and if you want to do it that way, that's more you're welcome to it. Nothing wrong with it. So here, my L is going to be negative 23 plus or minus the square root of negative 23 squared minus 4 times 1 times negative 990 all over 2 times 1. So I'm going to have 23 plus or minus the square root of negative 23 squared minus 4 times 1 times negative 990 comes out to be 4489 over 2. And 4489, and you have a calculator, you can always try it out, is a perfect square. It's 23 plus or minus 67 all over 2. And so 23 plus 67 is 90 over 2 is 45. Or 23 minus 67 is a negative 44, which is negative 22. Now, I get two solutions here. Obviously, this one does not make sense, because I can't have a negative length. It doesn't make any sense. This is what we would call an extraneous solution, and we'll talk more about those in other types of equations. An extraneous solution is one that comes up when you do everything correct, but there's some facts that you had to assume along the way to keep that from that cause an extra solution to come about that in the end doesn't make any sense. And in this case here, if the width is less than is 23 less than the length, then I know that the length is always going to be bigger than the width. The fact of the matter is, I would get two solutions if it could in fact be bigger, but not the way it's been defined. It's not going to be. So L equaling 45 is the solution. So when it asks what are the dimensions of the room, well, I know one of the dimensions is 45 feet. And now I know that this is 45 minus 23, which is 22 feet. So the dimensions of the room are 45 feet by 22 feet. So that's an application you could do. They also will give you some other ones that are a little bit more, logical in nature and more just algebraic. So let's have a look at example 6 and example 7. You're given the quadratic equation kx squared minus 5x plus 7 equaling 26. And they tell you that one solution is x equals negative 3. They tell you to find k and then find the other solution to the equation. Well, I mean, they get this said, if one of the solutions is negative 3, find the other solution to the equation. Knowing that along the way you have to figure out what k is, okay? But, in both cases, I'm just going to handle this. Knowing that this is a solution means that, if I put negative 3 in for the x's on this side of the equation, on the left-hand side, it should make the equation true. What that's going to do is give me another equation. So for A, based on the information I'm given, k times negative 3 squared minus 5 times negative 3 plus 7 should equal 26. So 9k plus 15 plus 7 should equal 26, which means that 9k plus 22 should equal 26. Subtracting 22 from both sides means that 9k is going to be 4, and k is going to equal 4 over 9. So that's part A. Now that means that when I do part B, and I'll go to a different color for that, my equation, my formula now is 4/9 x squared minus 5x plus 7 equaling 26. Now I'm going to have to use some sort of method to solve this equation. Whether it be, now I know that the way that it tends to work with quadratics, I mean, I have one solution that's already -3. Either -3 is going to be the one and only solution to this, which means that, you know, it's going to be rational, or it's going to be some other number, and since, you know, they come in pairings. If one's rational, the other one has to be rational, since, you know, we're talking about having integer coefficients here. You know, if one was if it was, I'm not going to have a non-real answer. I'm not going to have an irrational answer. So I could use some factoring. I could use, you know, any of the methods at all here. I just have to make sure that whatever method I use, you know, that this x equaling -3 does become a part of it. And, you know, if I'm doing factoring, keeping in mind, if x equals -3, that means that x plus 3 would have to have equaled 0, which means that if I'm using the factoring method, I would expect to see an x plus 3 come about. And that could come in some use here, because it might be something I could say, okay, well, that's what I'm hoping to factor out here. That's what I'm hoping to see what will become of it. You know, so I know what one of the factors are, and that can help, you know, make the process of factoring, if I choose that method, to be much less than, you know, other than using it than the other methods we've done. And so that's the way I'm going to do this. I'm going to use factoring. So I do want to get this set equal to 0. So I'm going to do that. And if I take 7 minus 26, I'm going to get a minus 19. But another thing I'm going to do, and you might say, well, why would you go about doing it that way? Why would you do that? I don't like having that fraction of 4/9 there. I mean, that seems to cause me some issues. You know, one way I could handle that is by multiplying everything by 9, but that certainly wouldn't make the numbers bigger. That'd be the trade-off, though. I'm going to keep the fraction in the long run, because it's going to keep the numbers smaller. But if you don't like having fractions involved, you can certainly multiply this entire equation. That means all three terms on the left by 9, and multiply the 0 on the right by 9, which of course will do nothing on the right-hand side, and just have integers. But that's going to give you more factors to worry about. But what I'm going to do is say, okay, well, I know I'm going to have a 4/9 x and an x to get that 4/9 x squared. And I know I want to have an x plus 3 here. Because I mentioned before, if x equals -3 was a solution, that means x plus 3 would be a factor of this equation set equal to 0. The thing I had to think of now is, well, what would I what would I multiply 3 by to get a -19? Well, I'd have to have a minus 19/3 here. And the thing I would want to do with this is make sure, well, with this, if I FOIL this out, will I get the 4/9 x squared minus 5x minus 19? So the first thing I want to do is do a double check and say, okay, well, if I do FOIL this out, I'm going to have 4/9 x squared plus 4/3, 4/9 times 3 is 4/3, x minus 19/3 x, and of course the minus 19/3 times 3 is going to give me a minus 19. These two combine together and give me a -15/3 x, and 15 over 3 is 5, so that is a minus 5x there. So I did confirm the fact that if I FOIL that out, I do get the equation that I had in this previous step. That's great. This means that this is my other factor. And since the x equals -3 came from this one, the other solution is going to come from this one set equal to 0. So 4/9 x minus 19/3 had to be set equal to 0. Adding 19/3 to both sides. Scooch this down a little bit. As far as the rest of it goes, I could recognize I'm multiplying by 4 and dividing by 9 and do it in separate terms or do it in separate steps. If I'm comfortable with my fractions, I recognize that multiplying by 9/4, multiplying by the reciprocal is the same thing as dividing, and that would make the 4/9 go away. So I'm going to multiply this by 9/4 as well. I get some cancellations occurring with that. The 3 here, this becomes a 3. And so I'm going to have essentially 19 times 3, which is 57 over 4. And 57 divided by 4 will come out to be like a nice little decimal, 14.25. And that would be the other solution. So that's me choosing to use factoring as a method and using some shortcuts along the way based off of me knowing some stuff. I could have just, taken the 4/9 x squared minus 5x minus 19 is equal to 0, use the quadratic formula, and should see the -3 come out as an answer, and then the 57/4 or 14.25 should come out as the other answer. That's another way of handling it. Example 7 is a very similar one, except now it has many more k's involved. You're given a quadratic equation which is kx squared minus kx minus k equaling 33, and one solution is 4. They want you to find k and then find the other solution. So again, for part A, I know that 4 is a solution, so I'm going to have 16k, that should be an equal sign here, 16k because 4 squared is 16, minus k times x, or it's going to be 4k because the x was 4, minus k equals 33. 16 minus 4 is 12. 12 minus 1 is 11. So I have 11k equaling 33. So k is going to equal 3. So when I start into part B, my equation is 3x squared minus 3x minus 3 equaling 33. Now, I'm going to just choose to use a quadratic formula on this one. So I'm going to subtract 33 from both sides, because the quadratic formula, I still have to have it set equal to 0. I also notice that all three terms are divisible by 3. That certainly will make the numbers a little smaller and easier to work with as I use the quadratic formula. So I'm certainly able to do that. If I divide both sides in their entirety by 3, x squared minus x minus 12 should equal 0 as well. So my a value is 1, my b value is -1, my c value is this. So as I go through this process, now I should still expect to see x equals 4 come out as an answer when I do this. So I'm going to have negative b, which is -1, plus or minus the square root of b squared, which is -1 squared, minus 4 times 1 times -12 all over 4 times 1. And again, you could use factoring or completing the square on this. I just chose to use quadratic formula. So I'm going to have 1 plus or minus, well, -1 squared is 1. 4 times 1 times -12 is a -48. So I have 1 minus a -48, which is 49. All over 4. Oh, no, sorry, take that back. That should be 2a, just 2. Over 2, I was about to say. And so that gives me 1 plus or minus 7 over 2. Well, 1 plus 7 is 8 over 2 is 4, which I expected. So this one I already knew about. 1 minus 7, however, is negative 6 divided by 2 is negative 3. So the other solution is negative 3. And that's how you'd go about solving that one. So, and that's the end of this video. It's a rather lengthy one because there's a lot of facts to go through with this and procedures. And I wanted to make sure to give you enough time with each one of them to have a look at them and know the difference between the two, practice them enough so that you know which one you're most comfortable with. You are expected to know how to handle each and every one of them. But ultimately, if you're just given a quadratic equation to solve and that's all you're asked to do is solve it, then any method at all you choose is acceptable. That's all I have for this video. If you have any questions on any of the things that were talked about in this video, please make sure to bring it up in class or come to my office hours. Until I see you in one of those places or until the next video, I will see you around. Have a good day.